Hello friends. So, in previous lecture we have learned about the concept of linear discriminant analysis, or in short LDA. In this lecture we will learn the Python implementation of LDA. Okay. So, for learning it we will make use of sklearn.discriminant analysis, and from there we will import linear discriminant analysis. Like in case of PCA, we have imported PCA from sklearn.decomposition. What we will do in this lecture, we will take a toy data set like we have done an example in the concept class, and then we will implement LDA on it, and then we will take a benchmark data set, and then again we will use linear discriminant analysis to reduce the dimension of that benchmark data set. We will also compare our result with PCA. So, if you can recall from the concept lecture, if you are having a two dimensional data set, let us say x1 and x2, okay, and these you are having these set of points. So, this set of patterns in this two dimensional plane, and here I am also differentiating these patterns based on their classes. So, blue patterns are coming from class 1, let us say, and red patterns are coming from class 2. So, what will happen in case of PCA? We will search for the direction of maximum variation. So, we will find a line in the direction where this data set having the maximum variation, and we will project all these two dimensional points onto that line to have a one dimensional representation of this data set. And if you see here, I will get this kind of thing. When you are having classification data, means you are having class information also. So, what will happen in 2D, you can separate this data by a linear classifier, okay, means by a line in two dimensional plane. However, when I will come to one dimensional representation of this data set after applying the principal component analysis, you can see I am having a mixed cluster. I cannot use a linear classifier now to differentiate this data into their respective classes. So, PCA preserve the variability within the data, but we lost class information. So, from the concept class, if you can recall, the solution of this problem is LDA. So, in LDA, instead of using the direction of maximum variation of the data, what we will see? We will see a line in such a direction. So, we will search a direction in such a way that after projecting the data onto a line having that particular direction, the data should remain the linear separable. So, for example, for this data set I will be having this kind of line. So, that all blue patterns will come here. So, these will be the projection, whereas red patterns will come here. So, I am having a clear distinction between these two, and this will be the line which is giving you the optimal separation between the class. When we see the difference between PCA and LDA, so I can summarize it with the help of this table. So, PCA do the feature classification, where LDA do the data classification, because here class information is also involved. We can see PCA as a supervised learning technique or feature extraction technique, whereas in case of LDA, we can use LDA as a supervised learning algorithm, means we can use it for classification also, where some unseen patterns can be projected onto lower dimensional space, and based on the cluster in which they are going, we can predict the class of those unseen patterns. In PCA, we search for the direction of maximum variation, whereas in LDA, we look a direction which provides maximum interclass separation. The another difference between PCA and LDA is, in case of PCA, I can reduce data up to any dimension, means if you are having 100 dimensional data, you can project it to a lower dimensional space, where the dimension of this lower dimensional space is either 50, 20, 10, 5, 2, 1, whatever you want to take. Whereas in case of LDA, we do not have such kind of flexibility. Here we can project the data up to the dimension equals to number of classes minus 1. So, if you are having 100 dimensional original data, which is coming, let us say, from 5 classes. So, I can reduce the dimension of the data up to 4 only. I cannot go beyond 4 like 3, 2 or like that. So, these are some major differences between PCA and LDA. So, now let us take a toy example and try to implement the LDA. Again, I will use Google Colab. Okay, so like that I have opened a new notebook in Google Colab. So, first I will define the data, but before that I will import some of the utility, like I will import NumPy as NP, because I have to import the data in terms of matrices. I will import matplotlib dot pyplot for plotting the results. Now, what I will do? I will define my 2-dimensional feature vectors. So, for that I will use a NumPy array and let me take data like 0, 1, 2, 3, 4, 5, 1, 2, 3, 3, 5, 6, 7, 8, and then let me also define the other row of this data. So, it will go 1, 2, 3, 3, so I have taken this synthetic data. So, this is the first column of the data, means x1 features, and these are feature x2. Total I am having 14 data points. Now, as I told you, here I should have class information also. So, I will give class information here again in a 1-dimensional NumPy array. So, let us take first 6 patterns from class 0 and last 8 patterns from class 1. So, I am having a binary classification problem, total 14 patterns, out of which 6 patterns are belonging to class 0 and rest of the 8 points are coming from class 1. let me make the column representation of this. So, I have taken the transpose of x and let us see the plot of this data. So, PLT dot scatter and I need to plot x. So, I need to plot all rows and first column as a x1 coordinate and then all row and second column as a x2 feature, and same time I will embed class information also. So, now you can see this data. So, it is a 2-dimensional data, horizontal axis x1, vertical axis x2, total 14 points, where 6 purple points are coming from class 0 and 8 yellow points are coming from class 1. Now, first let us apply PCA. So, if you can recall from one of the previous lecture, for applying PCA, I will import PCA from scalar dot decomposition. And then I will create an object. I will create an object of this PCA. I will define the number of components which I want to retain after projection. So, there are 2 components x1 and x2. So, I want to reduce it up to 1D. So, number of components equals to 1 and then I will do the fitting. So, PCA dot fit on the data x. Here I will not use any class information and then I will transform my data PCA dot transform and which data x. All these 14 points I will project onto the line, and again let me plot the 1-dimensional representation. Before that, let me check what kind of 1-dimensional representation I am getting. So, for that print the projected data. Sorry. Yeah, so you can see this is 1-dimensional representation of all those 14 points. If you want to see the plot, so the same command I will use, only instead of x now 1-dimensional data, and I am making a 2-dimensional plot along the line y equals to x. And now you can see 1-dimensional representation. So, you can see the mixed clusters. I cannot have linear separated data here, whereas in 2D it can be separated by a line here. So, PCA is not preserving the linear classification property of the data after projected in onto 1-dimensional space. So, now to get rid of this problem, let us apply LDA. So, for applying LDA, I will import the so from scalar discriminant analysis, I will import linear discriminant analysis, like we have done for PCA in earlier case. Now, let us define an object of this. Okay, so I have defined the object. Here you can give number of components, but I am going for the maximum one, 2-dimensional data, 2 classes. So, it can project onto 1D, and then I will apply LDA. So, LDA and dot fit, it will fit as well as transform the data. You can do it 2 lines also, first fitting and then transforming x, and here you have to give class information also. So, I am giving y also, and then you can see the plot of this after applying LDA, what kind of data I am getting in 1D. And then class information c equals to y. Okay, so this is the result. Now you can see all 6 points from purple class, that is class 0, are coming one, making a single cluster, whereas there is clearly linear separable cluster of all rest of the yellow points. So, if you take any threshold here, here or here anywhere, then you can make you can classify this data using a linear function, means a point in 1D, that on the left side of that point the class is purple, whereas on the other end of the point you are having yellow class, that is class 1. If you want to see the data one dimensional representation, so you can see here print and then x underscore LDA. So, you can see, and if you want to print PCA also, which we have seen earlier also. So, this is x underscore r. Oh no, not r, x r, not underscore. Yeah. So, like here first point is projected to means having representation minus 2.73, whereas in PCA it is minus 4.07. So, like that. So, from these figure you can get a good idea of the advantage of LDA over PCA. Okay, this is the toy example. Okay, for another example we will take a benchmark data set, that is a very famous classification problem data set called wine data set. So, this data set is the results of a chemical analysis of wines grown in the same region of Italy, but derived from 3 different companies. Okay. Then the analysis determined the quantity of 13 features or attributes found in each of the 3 types of wine. So, it means we are having 13 different parameters on which these wines were tested, and the wines are coming from 3 different classes. So, data set is multivariate, as I told you. We are having 13 features. The entities are integer or real. So, numeric data I am having. We will classify the wines to their respective classes, because I am having 3 classes, 3 different types of wine. Total number of patterns are or samples are 178. Number of attributes 13, there is no missing value. Okay. So, these are some information about the data set. So, now what we will do? We will having 178 patterns of this wine data set. Each patterns is from the input feature vector is 13 dimensional, coming from the 13 dimensional real vector space. And then what we are having? These 178 patterns are coming from 3 different classes. Let us say class 0, 1 and 2. What we will do? We will split this data into two subsets. One of the set we will use for training and the other one we will use for testing to evaluate the performance of learn classifier. Before that we will apply PCA because it is a 13 we will apply LDA because it is a 13 dimensional data set. We will reduce the dimension 2, that is the maximum minimum possible, because there are 3 class. So, we can go at most up to 2, we cannot go up to 1 dimension. 3 minus 1 equals to 2. Let us try to implement this particular, what I will say, implementation in Python. So, first I will import this data set. So, from sklearn dot data sets I will import load underscore wine. So, it is a part of sklearn dot data sets. I will import pandas as PD to see the different 13 attributes. I will also import matplotlib dot pyplot as PLT for the plotting purpose. So, these are some utility. We will import other utility at the time when they will be required in the subsequent cells. Okay, so, we have imported our utilities. Now, let us see the data set. So, first I will store in the array wine and I will run this function load wine. So, it will store all the data in wine, and then I will be having two parts of this wine. One is wine dot data for input feature vectors and wine dot target for the target values of these features. So, let me store it in x and y. So, np dot array wine dot data for so x will be now at 178 into 13 array, 178 rows and 13 columns, and then corresponding class information I will do it in y, np dot array y. So, y is 178 by 1 array. Let me run it. Oh, some issue. Okay, we have not imported numpy. So, import it. Yeah. Oh, this will be wine dot target, not y. Yeah, so this has come. If you want to see, print x and let me print some 4-5 rows. So, first 5 row 1 to 5 and all the columns. So, you can see 1 2 3 4 1 13, the first one, this is the feature vector for first sample. So, it is having 13 data, then the second one and so on. And similarly, if you print y, you will be having the class information of all 178 patterns, you can see. So, this much patterns are coming from class 0, first type of wine, these are coming from class 1, second type of wine and so on. Okay, so, we are having now our data. You can use you can see the information about this data. So, let me try to learn it. Yeah. So, this is wine data set, some pattern, and these are the feature names, the quantity of alcohol, malic acid, as all those kind of thing up to proline. So, these are 13 features, and then these are target, and these are class 0, class 1 and class 2. Now, first let me apply PCA and then I will apply LDA. So, you are quite familiar now how to apply PCA. First I will import scalar dot decomposition, okay, not import, from this package, from scalar dot decomposition import capital PCA, create an object, oh my god, create an object PCA equals to PCA. So, total there are 13 components, 13 features. So, let me define only means let me reduce the dimensions up to 2. Let me fit the PCA. So, small PCA dot fit, and what is my input data? X. Let me transform also, let us save it in Z, result dot transform and then X, and finally you plot the result, plot dot scatter Z, all columns, all row first column, because now it is 2 columns only instead of 13 columns. So, second column you can easily plot it, all row second column, and the same time I am embedding class information also in my plot. Yeah, so you can see. So, actually this data is linearly separable in original dimension, but when you will apply PCA you can see I am having mixed clustering of 3 classes, 3 types of wine. So, it is no more linearly separable in reduced dimensions, means in 2 dimensional space when you are applying PCA. In horizontal axis I am having PCA 1, principal component 1, on vertical axis I am having PCA or PC component 2. Now, let us apply LDA. So, apply LDA, first import this LDA from scalar dot discriminant analysis, import linear discriminant analysis, create an instance of it or object of it. So, linear yeah, it has come, and again I am not giving the class information, means number of components here one can give, but since I have to go up to maximum, means whatever possible, that is number of classes are 3. So, we can go up to 2 dimensions. So, it will by default will take 2. Now, X underscore LDA equals to LDA dot fit, and it will trend and project also, fit underscore transform X, and here you need to give class information also, and finally you can plot your result in 2D. So, all rows, and first column I will be having all rows, and second column C equals to Y. Okay, I hope it so done. let me try. Yeah. So, now you can see the difference. After applying LDA, the data is still linearly separable. So, originally you are having 13 classes, I have reduced to data into 2 LDA classes, LDA 1 and LDA 2, and still data can be classified using simply lines or linear classifier. So, you see how much information or how much computational cost we have reduced, coming from 13 dimension to 2 dimension. So, it is a very good example where PCA fails to preserve the linear separation property, but LDA preserve. Okay. So, this is one of the aspect. Further, you can use this LDA as a linear classifier also. So, for that what I will do? I will divide my data into 2 parts, one for training and another one for testing. So, for that let me call a function to split the data set. So, sklearn dot model underscore selection, and I will import train test split. Then what I will do? I will define x train, x test. So, I am dividing x into 2 parts, similarly y train and y test equals to train test split. And which data I am doing? I am doing my x, y, okay, done. And then you can give your test size out of 178 patterns, how many patterns you want to use for training and how many patterns you want to use for testing. So, that I can say like this, test underscore size and equals to 0.3. So, it means 70% data I will use for training and 30% data I will use for testing. Okay. Now, I will use LDA dot fit and I will train on the training data x train, y train. So, training I will do here. Yeah, so you can see training is over. Then I will go for the prediction on the testing data. So, let me write yn LDA dot predict and x test. Okay. So, now I am having this yn as the predicted class, whereas the original class is there in y test. So, let me see how many patterns I have correctly predicted and how many are misclassified. So, let me print the true classes which is in y test. Let me print the predicted classes using our LDA model. So, that is in yn, and let me print their difference also. So, y test minus yn. Yeah. So, these are the true classes of the testing patterns, 30% patterns of the 178 patterns. These are the predicted classes using our model, and this is the difference between two. You can compare these two array, all are the same entry, means all the data are classified into their true classes. I am having 100% accuracy. So, this is a wonderful model for linearly separable data. We have done the implementation. Okay. So, we have seen couple of implementation of LDA using sklearn dot discriminant analysis dot linear discriminant analysis. I hope you are having now idea how to implement LDA for dimension reduction and classification. So, let me close this lecture here. Thank you very much.